Hi everyone, my name is Sina Shah Hosseini. I'm a PhD candidate at University of California, Irvine. Today I'm going to present hybrid learning for orchestrating deep learning inference in multi-user edge cloud networks. Today, deep learning-based intelligence services are everywhere. In smart cities applications, healthcare domain, or autonomous vehicle systems. Intelligence services are computationally intensive by nature. That means resource-constrained user devices are not a good choice for executing these services. Cloud computing is a conventional solution for executing these services, but it comes with some drawbacks. It might not perform well with unpredictable network conditions, or sometimes some users might not want to share their personal data with cloud providers. Collaborative end-edge cloud architecture is another alternative for executing these services. It involves computing resources in the end-edge and cloud nodes to execute these services. It provides acceptable latency and quality of service for us, and the architecture relies on the computational offloading strategy, where tasks can be offloaded to any computing node through the end-edge cloud system. Computational offloading strategy is a complex problem by nature. Diverse system parameters such as workload computational complexity or execution target capability might affect the optimal computational strategy. It defines where to offload, what to offload, and when to offload the task. Besides that, a dynamic environment may affect the optimal computation strategy. For example, when we have a poor network condition, the situation might lead to local computing, while we have a strong network condition, the cloud computing might be an optimal computing policy for us. Therefore, finding the optimal strategy is known as the NP-hard problem. Assume that we have an end-edge cloud system that runs a simple classification application. We want to demonstrate the effect of dynamic environment and diverse system parameters on optimal orchestration policy. In Figure A, we evaluate the simple classification in two different network conditions. We have regular condition and weak condition. Y-axis represents the response time in milliseconds. Blue bar represents local or device computing, where the computation is performed at local device. Green bar represents edge device computing, where the classification is performed at the edge device, and red bar represents the cloud computing. In a regular network condition, cloud computing is the best solution with the lower response time. But when we have a weak condition, local computing shows better performance with lower response time. In Figure B, we evaluate the response time of the system in presence of a different number of users, from 1 to 5 simultaneous users. The figure shows increasing the number of users directly affects the performance of edge and cloud computing. A single user can offload the task optimally to the cloud, but when we have 5 users, cloud computing is not an optimal solution anymore. In Figure C, we present the trade-off between accuracy and performance. We have a diverse set of classification models, DL models, with different computational complexity and different accuracy. Better performance comes with lower accuracy. So, there is a trade-off between performance and accuracy. In task orchestration, we might want to keep the computational local, and it comes with sacrificing the accuracy of classification. Therefore, a dynamic environment and diverse system parameters provide a complex orchestration problem, which is known as NP-hard problem. This figure shows an end-edge cloud system architecture. On the left side, we can see different computing nodes: end node, edge node, and cloud node. On the right side, we can see virtual system stack layers. We have the hardware layer at the bottom, which represents the hardware capabilities. The network layer represents network conditions, and platform layer represents the node's resource availability. In the application layer, we have deep learning application parameters such as model parameters, computational complexity, and model accuracy. For example, the model's parameter can be represented in floating point format or integer format. To address the complex orchestration problem, like what we discussed in last slide, we need an intelligent agent to optimally orchestrate the task. The decision intelligence block located at the cloud node can observe the environment situation and makes a decision and apply the optimal action as orchestration decision. In this paper, we implement a runtime reinforcement learning-based orchestration framework for deep learning inference services in order to minimize the response time within the accuracy constraint. Also, we propose a hybrid learning algorithm to accelerate the reinforcement learning process and reduce the direct sampling during the learning phase. From what we said in the previous slide, the orchestration problem requires intelligent runtime management to search through different configurations. Reinforcement learning approach has been used for orchestrating deep learning inference tasks in end-edge cloud systems. We can classify reinforcement learning approaches into two different categories: model-free approach and model-based approach. Model-free approach operates with no assumption about the system's dynamic and also consequence of its action to learn a policy. Also, model-free builds the policy model based on data collected through trial and error over the epochs. Because of the mentioned trial and error learning, model-free reinforcement learning approach requires too many interactions with the environment. These too many interactions with the environment are not feasible in computer systems because first, each execution is very expensive. It results in higher latency, resource consumption during the learning process. On the other hand, model-based reinforcement learning uses a predictive internal model of the system to find the outcomes. It avoids the consequence of the mentioned trial and error in real time, which leads to have a computationally efficient approach and also providing better generalization for us. It requires significant fewer real full execution before it reaches to the optimal point. On the other hand, as a disadvantages, model-based reinforcement learning is sensitive to model bias, and also it suffers from model error between what it predicts and the actual behavior. It leads to suboptimal orchestration decision. In this paper, we propose hybrid learning. The hybrid learning approach integrates the advantage of these two approaches, model-free and model-based reinforcement learning. So hybrid learning is a combination of model-free and model-based reinforcement learning. This figure shows the hybrid learning architecture. It consists of system environment block, system model block, and policy model block. The training process starts with an initial system model and initial policy. The agent is trained in three phases. First phase is direct RL. It is simultaneous with the second phase, which is system model learning, and then planning as the third phase. In the direct RL phase, the agent interacts with the system environment to collect real experience for training the deep network model. So it executes the DL inference on real system to collect real experiences. During the system model learning, we model our system to predict the system's behavior. So as the agent takes more steps with real experience, which is direct RL, the model learns the system from state action pairs that have been experienced before. During the planning phase, the agent uses the system model to predict the system's behavior and use it to improve the policy model. Therefore, in this strategy, after sufficient real experiences, the system model can predict the system behavior. The agent relies more on systems model prediction rather than real experiences, which is costly for us. Our online learning framework is implemented in three-layered N-edge cloud architecture. We have up to 5 end devices, 1 edge device, and 1 cloud. Our agent, RL agent, is located at the cloud. We consider up to 5 user requests simultaneously for a DL service. Each user device runs 2 services at the same time. First, intelligence service, which is a DL classification on our evaluation, and also the second service is resource monitoring application. So the resource monitoring application observes CPU utilization and available memory and also network condition. Then it broadcasts the status of the system considering the CPU utilization, available memory, and network condition with the RL agent, as I said, located in the cloud. The RL agent considers this status, resource availability of all devices as state and chooses appropriate action. The action is a combination of deep learning models and execution target, which can be local computing, edge computing, or cloud computing. The agent considers average response time as a reward. So that means that the agent tries to minimize the average response time in our scenario. In this slide, we explain the experimental setup. We have a pool of DL models for image classification service. Each model has different computational complexity and prediction accuracy. For example, we have a model with high accuracy prediction, D0 with 569 million max. Also, we have a quantized model, D7 with 72.8% prediction accuracy and 41 million max complexity. Also, we evaluated our proposed solution within different environmental setup. Experiment A to D represent a diverse set of network conditions. Experiment A represents a situation where all devices are connected to the network with regular condition. But experiment D represents a situation where all devices have weak network connectivity. We evaluated our proposed solution in 2 aspects: agent performance and training overhead. For agent performance, at design time we determine the true optimal configuration for orchestrating a DL task under any given condition of workloads, network condition, and the number of active users using a brute force search technique. RL-based orchestration decisions always converge with the optimal solution. Here we investigate the agent ability to find the optimal orchestration decision under different scenarios of varying network conditions. We have experiment A through the experiment D with different accuracy constraints. In experiment A with minimum accuracy constraint, agent chooses to keep the execution at local device. But by increasing the accuracy constraint, the agent decides to offload the computation to the upper layers, like edge and cloud. Therefore, changes in accuracy constraint result in different execution target and selected DL models. On the other hand, changes in environmental setup, network condition result in different orchestration decisions. For example, in experiment A, where all devices are connected to the network with regular connectivity, to experiment D, where all devices connected to the network with weak network condition, results in different execution choice and different model to be selected by our agent. We have compared our work with the state-of-the-art works that applied reinforcement learning to orchestrate deep learning at end-edge cloud architecture. Autoscale uses model-free approach with Q-learning algorithm. Also, Adadip uses model-free approach as well with deep Q-learning method for inference orchestration. These 2 work use different knobs in their framework as actions. We evaluated our proposed solution in terms of training overhead and compared with the state-of-the-art works, Adadip and Autoscale, which mentioned in last slide. The framework is evaluated in presence of different number of active users and different accuracy constraints. For example, green line represents maximum accuracy constraint, blue line represents 85%, black line represents 80%, and red line represents minimum accuracy constraint for 3, 4, and 5 end devices. Y-axis represent the reward, and x-axis represent the number of steps which is taken to reach to the convergence point. Also, deep Q-learning represent the state-of-the-art Adadip work, and hybrid learning represent our solution. Here is the summary of convergence time for different number of users through different accuracy constraints compared with autoscale and autodiv. For 5 users through a different number of constraints, our hybrid learning approach accelerates the training process by up to 11.6x and 166.6x in comparison with the state-of-the-art autodiv and autoscale respectively. We also present the overhead of training agent in finding optimal orchestration decisions with experience time and computation time metrics. Experience time is the total time to execute all taken steps, a cost of interaction with the system environment to identify an optimal policy. On the other hand, computation time is the time to train the agent. The hybrid learning algorithm results in 4.4x and 9.4x speed up in comparison with autodiv for computation time and experience time respectively. In conclusion, in this work we present a reinforcement learning-based framework for orchestrating DL inference at end-edge cloud architecture. We propose hybrid learning and an integration of model-free and model-based reinforcement learning approach for DL orchestration framework. Our evaluation showed that hybrid learning results in fewer number of interactions to converge to an optimal solution. Also, we showed that it is significantly faster than other state-of-the-art model-free approaches. Thank you for listening to this presentation.